Okay, so now I want to talk about an SN2 reaction. So this is typical SN2, primary chloride, excellent nucleophile, but still pretty slow at room temperature. Okay, it turns out that when you add a little bit of sodium iodide, your reaction gets a lot faster. Okay, catalytic amount, again, it's a tiny amount. Iodide does not show up in the product at all. How should we understand this? Well, you got to know two things about iodide. One, iodide is a great nucleophile. It doesn't really form strong hydrogen bonds with solvent. It's really big and diffuse and polarizable. It is fantastic at displacing chloride. But once it's done that, iodide is also a great leaving group, right? It's a stable anion on its own. It's not too basic. That carbon-iodide bond is very weak. And so it's a weird thing where it forces its way on, but then it's easily forced off. So great nucleophile, great leaving group. And so you're going to end up with iodide free to then go and re-enter the catalytic cycle. Sometimes this is done in two steps because we take advantage of the fact that sodium iodide, NaI, is soluble in acetone. Which is kind of weird, right? It's a salt, technically, but it is soluble in acetone. So when I do this reaction, it's kind of like that silver example I showed before, where even though you'd think it'd be in equilibrium, it ends up being entirely over to product because chloride grabs sodium and precipitates. You see salt form in acetone. And so this is going to drive it entirely to the iodide product, which again is now a fantastic leaving group for any nucleophile I might want to bring to bear. Here I'm using cyanide, and that's a pretty easy reaction to run. Okay, so one more observation of a weird rate thing. So this is the one in red is a beta-chlorosulfide. So if I compare that with the chloropropane above it, I can see that if I treat both of those with water, the top reaction is very slow, but the bottom reaction is actually pretty fast. Okay, what kind of reaction is this? Well, I mean, first you'd say, well, I'm looking at water. Water is a bad nucleophile. I'm looking at a primary chloride. Can't really form it seems like it can't form a cation. So it would seem like either SN1, SN2 are both out. SN1's out because I've got no stable cation. SN2 is out because I got no good nucleophile. But yet the bottom reaction happens, and pretty quickly. How? So what happens here is almost going back to our epoxide thinking. Sulfur is leaning over and kicking out that chlorine, making that a three-membered ring. Again, even though that's strained, it does happen fast. Kinetically, it's favored because it's sort of stuck there. Once you form that three-membered ring, now that's a very reactive electrophile. And water can come in and displace that. This is sort of an SN1 reaction, right? Because the slow step happens with one molecule and a weak nucleophile traps the cation. Okay, so it's SN1-ish. Sometimes we call this neighboring group assistance, right? So the sulfur is leaning over, kicking out the leaving group, allowing for easy nucleophilic substitution at either carbon, because both those carbons are equivalent now in that intermediate. So why does this matter? This is how mustard gas works. So mustard gas was a devastating chemical weapon used pretty widely in World War I. Forms incredibly painful lesions on the skin. If it's breathed in, it wrecks the lungs. Just an awful way to die. Wilfred Owen wrote the poem Dulce et decorum est about what it's like to be in combat and be exposed to mustard gas. He was a poet that died in World War I. And so this is how it works. A mustard gas looks like that. It's got chlorines on either side of the sulfide. DNA has tons of amines all over the place. It's going to alkylate DNA, which arrests the cell cycle and cells die. Okay, so it was known pretty early on that the medics saw that when soldiers came back exposed to mustard gas, these awful lesions, that if you looked at their white blood cell counts, they were flatlined. There was very, very low white blood cell counts. And so that gave people the idea that actually lymphoma is cancer of the white blood cell. And so this might actually be a useful way for us to treat cancer of the white blood cell. And people weren't in a hurry to try that because it seems like a tough ask to have a cancer patient take mustard gas, but it did happen in the 1940s at Yale, and it showed that yes, if you literally drop mustard gas on tumors, which I can't imagine anything more painful, but it's going to shrink the tumor. And so this was essentially the birth of modern synthetic chemotherapy for cancer. Now, obviously, we don't want to have mustard gas in the clinic. And so the first thing we did was go to a slightly less nucleophilic atom in the middle. That's nitrogen. Nitrogen, it's called mustine. It's still a little bit too reactive. That lone pair is a little bit too nucleophilic. So we want to knock it down a bit. The next round of synthetic changing it was to put a benzene ring on that nitrogen. So picture that lone pair on nitrogen. Now that lone pair is conjugated into the benzene ring. And so it's a little bit less basic, a little bit less nucleophilic because it is spread out more. So now the reactivity seems a little bit safer, a little bit less byproducts, but now we've got a water solubility problem. It's too lipophilic. It won't get into the bloodstream like it needs to. So we need to engineer something like this that is more water soluble. So take a second, maybe stop the video here and think about how you might do this. How might you engineer a molecule that does what this does, but is more water soluble? Here's what they did. They put a carboxylic acid on this compound. So now it's a really, really nice hydrogen bond donor. It's going to be much more polar. Now our solubility issue is good, but now it's actually not reactive enough. Why is that? Well, again, think about resonance. That lone pair from nitrogen is now conjugated all the way down into that carbon-oxygen double bond. And it's really delocalized. So now we've drawn too much electrons away from nitrogen, and so it's not quite as powerful enough. Okay, so again, challenge to you. Iterate. How are we going to keep something that's water soluble, but fix this problem that we've made for ourselves of deactivating our nitrogen lone pair? Well, nobody said that these hydrogen bond donors needed to be conjugated to the system at all. So let's just throw a couple carbon CH2s in there, some sp3 carbons. Now the carbonyl is not conjugated to the nitrogen. So we've got our hydrogen bond donors for solubility. We've got our reactive lone pair. This is chlorambucil. This was used in the therapy for a long time. This is a chemotherapy drug for lymphoma. In the modern day, there are several mustards that are used in chemotherapy. Cyclophosphamide is a really common one used in combination therapy, particularly for, I think, breast cancer. But uracil mustard, phenylalanine mustards, many of these are derivatives of biological molecules that kind of help the body get it to where it needs to go. But every time we see these mustards, again, if you look kind of through the fossil record, if you will, these are all derived from mustard gas, chemical weapons in World War I. So this is how chemotherapy started, by observation and by careful tweaking of the mechanism and understanding the relationship between structure and reactivity.